Hey, this is Brock Lemire's, and in this video I'm going to talk about sources of electric energy and specifically the electric generator. Okay, so we've kind of talked about that there's three main techniques that humans use to obtain electric energy, and that's the battery, the electric generator, and solar cells. And these three make up the vast majority of sources of electrical energy that we use in society. And so I want to specifically focus on the electric generator. Okay, so in the 1800s, a scientist named Michael Faraday noticed an interaction between magnetic fields and electric circuits. So a magnetic field, I think we're all aware of what a magnet is, but it's one of these contactless forces that exists in nature where you have some materials that exhibit this property where they are attracted to each other. And so when you have a magnet, you have a north pole and a south pole, and it will, they'll attract each other. Okay, and so what we do is we define a magnetic field, which is kind of this contactless force or invisible force between the north and the south pole, and we give it, in electrical engineering, electromagnetics, we call it a B field, so we give it the letter B. And so this is pretty cool because you can just find these things, laying around Earth, and you can also make them. But this Michael Faraday noticed that if you moved a charge through a magnetic field, okay, and now you think about charge moving. Well, charge moving can be current, right? So current is electrons moving, electrons have charge. And so it can either be just a single particle of charge that flies through here, it can be a single electron, but whatever it is, if charge moves through this field, there will be a force that is exhibited on it, okay? And the force is given by this Fleming's left-hand rule. And so you can basically take your hand and you can say, okay, take your left hand, make this little, two with your thumb sticking out, and you put your index finger in the direction of the magnetic field, you put your middle finger in the direction of current, and then your thumb points in the direction of motion. So in this figure right here, what you do is you'd have the magnetic fields going from left to right, the current's coming out of the screen, and then you'd have a force that pushes up on this. Okay, and this is like the birth of electromagnetics. Okay, so you have electricity, electric flow of charge, and magnetics, and their interaction. And their interaction, it turns out, is in the form of fields. And so it's pretty awesome. So electrical engineers were like, well, if you need to move charge, why don't I put charge in a wire? And I can move electrons as the charge. And guess what? If it's a physical wire, we can move the wire. And so you can actually take a physical thing, and as long as you run current through it, a physical wire will move. Okay, it will physically move. And so it's like, oh, this is unbelievable. So then what do engineers start doing? Well, we're like, well, check this out. If you use that same logic, what if we put a loop of wire? And if you did a loop of wire and you ran current through it, what would happen is that the current flows in one direction. So you'd actually have current flow up the wire, turn around and come back. And since it's moving in a different direction due to that Fleming's left-hand rule, you'll actually get a force that's opposite on this loop. And so what happens then is that you start getting rotation. And all of a sudden we find that the electric motor is born. And so engineers got together and they started designing these things, and they figured out, oh man, this is so cool. We just need to make, find these magnets, and we'll shape them into something round, and we're trying to basically make something spin in here. And so this is what a motor is, all right? And so obviously it takes some techniques. If you apply a DC voltage on here, one of the things that has to happen is you have to apply, the current a certain way, and then as soon as the loop of wire gets up to the top, you have to reverse the direction so that it'll get pulled down, and then reverse it again and it'll get pulled up. And the whole field of like motors is a whole thing in itself. And so the term electric motor is a device that converts electric energy into mechanical energy. And it's in its simplest form, it is current in. So we put electrical current in and we get rotation out. And that rotation comes from this whole property of electromagnetic interaction and the force that is exhibited on a charge that is moving. And so all this understanding of these interactions between magnetic fields and current flow and forces, this is all governed by what we call Faraday's law of induction. And so Michael Faraday was the one that kind of put together the framework for this and came up with the math behind it. So we just kind of use this term Faraday's law of induction to kind of describe this entire phenomenon. Okay, so let's take a look at some modern day uses of this, or just some examples of this. So here's a little board that we use to teach electromagnetics or just demonstrate electromagnetics to people for the first time. And so what I have here is, this is a motor, a motor, or excuse me, this is a magnet, and it's like a really strong magnet. So if I put any sort of material that's attracted to magnets, it'll stick. And this is essentially like a half motor, because I have 9 volts. So I'm going to apply 9 volts, and what I do is I have these little things that come up, and they can hold something that can spin. And so I put this 9-volt battery across these 2 terminals. And if I look at what I essentially have before I get it spinning, is if I just look at this, I have 9 volts across these little paperclip things. Okay, can't see that very well. See that? Okay, so you got that. All right, life is good, and you see 9 volts. My battery's getting low, but 7.5. It'll still work. Okay, so we have this 9 volts in here, and then what we do is, this is a coil of wire, and what we're going to do is, if I put it in here, I've scraped off, it's a piece of copper, and what you do is you wind it so that each time the current flows in this loop, it gets, each wire gets a certain amount of force depending on the magnetic field strength and the voltage across it. And what'll happen is that by winding it, you get force on each wire. So it gets stronger and stronger and stronger. And then what I did is I scraped off half of the coating on here so that it can actually make contact with this. And so what this looks like is, it's actually 9 volts going through this wire right here. And so then it doesn't quite have enough force to start getting it spinning, but you can kind of see that it's trying to move, and if I just give it a little push, it starts, and now it's just sitting there spinning, and it's like, oh, this is awesome. And so it depends on how far you have it in there, but this is kind of like the whole, there's a motor, and it's kind of a half motor, because the magnetic field coming out of this battery, or the magnet on the bottom, is literally, the magnetic field comes up and it actually goes back down into the earth. It would work a lot better if I had another magnet on top. Okay, so that's just a quick example of showing that this is real stuff. I mean, I'm sure you knew it was real stuff, but this is real stuff. And then of course, people have built motors that are a lot more compact and a little bit better than this little demonstration. This just shows kind of the inner workings of it. So this is an example. This is a little DC motor here, and I put a little piece of cardboard on it so you can see it actually spinning. But if I just take this and I put if I put this across if I put a voltage across it, I mean, the thing just starts flying, right? So let's see if I can get that on there. Oh, look at that thing. Yeah, so there it is. I mean, this one has magnets in a circular form, but this is the exact same thing. It's Faraday's law of induction, and you apply electricity to it, and you get motion out. So that's awesome. That is an electric motor. But now we can finally turn our attention back to what we're talking about, which is, where do we get electric energy? And it turns out that the electric motor works the same way in reverse. So in a motor, you put in rotation, you get electricity out. Well, if you put rotation in, you get electricity out. And so that is what an electric generator is. And so if we can find some way to spin the coils of wires within the magnetic field, we will get current out. And so it's awesome. It's the exact same thing. And so let's take a look at an example. So here's our little motor again, right? Here's our DC motor. And if I come over here and I'm going to hook it up in current mode, okay? And I'll go ahead and clip onto this thing. And we'll just see if we see anything kind of come out. We'll spin this, then we'll see if there's any current, right? So we got that there. I got it on milliamps. I got it in the current setting. You can kind of see there, I got it on 20 milliamps. And I pick this thing up and I start moving it, and it's like, look at that. I'm starting to see current. And if I spin this thing, look at that. I'm seeing current come out of here. And this is unbelievable. So that means if we just rotate this thing, we actually get current out, okay? And so yeah, I mean, in case you don't believe me, Let's just keep going. So let's take a look at this thing. So here I have my breadboard, and I have on here, I wired up a little light emitting diode right there. And what I'll do is I'll see if I can get it to flash, or at least light up a little bit as I spin this. So I'll clip on my 9, so that's one side of the little light, and then the other side I'll clip. A little harder to clip than it looks, huh? So we got boom, boom, boom. I got them clipped, and then I'm gonna come over here and I'm gonna clip this on there. So I should have something, okay? And so now I'm gonna sit here and I'm gonna see if I can see any light out of that thing. And let's see. You see that? So you see that little light coming on here? So you look at that little LED right there. So you're gonna look at right there and see if you can see it flash. Do you see that come on? Now watch this. And the faster I spin it, the more it comes on. And it's kind of hard to see. Let me one more day. Let me get it really hard. Now you're sitting here going, that's really awesome. Well, notice that I can't keep this spinning fast enough. So it's like I can't physically spin this. I mean, if I could like hook it to an exercise bike or something like that, it'd be one thing. But that then just brings us flat out to all we need to do is find a way to spin this motor. And so what we are trying to do with electric generation is we are trying to find ways in nature that we can make the thing spin so that we can have electricity provided to us. So let's take a look at sources of how we can obtain mechanical energy. And let's start with the big one. This is where almost all of our energy comes from, which is boiling water. It sounds simple, doesn't it? So what you do is you need a source of heat and you boil water and you make it into steam. So the steam expands and it's super hot and it's actually pumped through fins, or a turbine, and it'll actually cause it to spin. So all you need to do is find some source of heat. So that is literally where almost all of our electricity comes from. It's just boiling water to make steam, which in turn expands and spins a turbine. So now here's the trick of it. How do you boil water? And that's where you start seeing all these different sources. This example right here is a coal-fired power plant. They dig coal out of the ground and they burn it, right? And then the burning boils the water and then they spin a turbine, okay? Another way to, and there's other sources too, like nuclear. All they're doing there is they're taking radioactive material and boiling water and making it into steam and spinning a turbine. Natural gas generators, same thing. Burn natural gas, burn natural gas and make steam. Okay, but it's all the same thing. You're just trying to boil water. Another one, which is really cool, is a hydroelectric dam. So if you build a dam and you have this reservoir that sits behind it, you have all this kinetic energy of the water, and so you allow it to flow through a pipe, and then what it does is the water flows through and it spins a turbine again, and then that turbine spins a generator, and then electricity pops out. So as long as you have water flowing down this pipe in the dam, then you have electricity, and that is a hydroelectric power plant, okay? But it's the exact same thing. All you're doing is finding rotation in energy and, letting it spin a generator. And then you got the wind turbines, right? So then imagine just taking a generator and setting it up on a big pole and putting fins on it. And so then the wind blows and it spins the generator, and here we go, and off we have it. Okay, so that's what it's all about. All right, now let's take a step back and let's think about where does all of the electricity come from? When we talk about generation, this is the stuff that's in the walls. We call it the power grid. And it's important because you have electricity in your outlets, but it's only there as long as things are spinning. If all the spinning stops, then there's no electricity. So this is real-time delivery of energy. Now, if you look at the sources of electric generation, this is all the powering the grid. Look at where it mostly comes from. Natural gas is 38%. That is burning gas to spin a generator. Then you go to coal. That's burning coal to boil water and spin a generator. Natural gas, burn gas, boil water, make steam, spin a turbine. Coal is burn coal, boil water, make steam, spin a turbine. Nuclear, use radioactive reactions, radioactive reactions to boil water, spin a turbines. Then you finally get up into renewables, and the classification here is basically nuclear, coal, and natural gas. These are kind of like, we don't consider these clean or renewable. They're kind of coal, you know, you make smoke and all this stuff. Natural gas, we're pumping out of the ground. Coal is like limited. Petroleum's actually in here too. You burn just oil and gas. But let's look at renewables. So you're like, oh, finally we get to something alternative, some alternative. Well, it only makes up 17% of all the power in the grid, but look at it. Here's your wind. It's 7.3. Hydroelectric, 6.6. Again, just spinning. Solar, that's interesting. Very small, but that is the only one that's not spinning, but it's actually kind of cool. And we'll talk about that in a later video. Biomass, you're like, what's biomass? That's like burning wood. Okay, so that's just like you pick up leaves and wood and burn it, boil water, spin something, and then you got geothermal. So you use the heat coming out of the ground to spin it. But it's all about spinning a generator to create electricity for us. Okay, so that is it. That is our second main source of electrical energy, which is the electric generator. See ya.